Now, in terms of size comparison of single reactors, we're going to discuss first about the batch reactor. And the batch reactor, as we all know, is only suited for producing small amount of material or processing a small amount of feed. Now, it's also suited for producing different materials from one piece of equipment. So in terms of convertibility and versatility of the reactor itself, there's no question, because anyhow, what we do with the batch reactor is we place the reaction mixture inside, let it proceed, let the reaction proceed, and then take it out once the degree of conversion was already achieved. So it can process varied types of feed, not only limited to a particular type of feed. Now, for epsilon A equal to 0, and for, shall I say, fluid systems, this is the case. Constant density system, fluid reacts in the same amount of time in the plug flow and the batch reactors. Thus, for these two reactors, the same volume is needed to do a particular job. The same volume or the same size of reactor is needed for the batch reactor and for the tubular reactor when we speak of the same type of reaction, as long as it's a constant density process, meaning the volume is not varying. So the same size requirement for the tubular and for the batch reactor. Now, in terms of instrumentation cost, since its requirement is very small for auxiliary equipments for it to be operated, it's small. And in terms of operation, there is flexibility and there's versatility in terms of the use of the reactor itself. The downside are those that are written in red font. So high labor and handling costs because of the charging and the withdrawal of the feed that was already processed inside the reactor. And there's not much, shall I say, there's not much of what the operator can do in terms of the quality of the product that will be withdrawn from that particular reactor given the time in which the expected conversion is going to happen. So meaning, mahulat na lang siya kung anong matabo, kung pila ang degree of conversion na matabo for a given time for a particular reaction that is facilitated inside the batch reactor. Unlike the flow reactors in which there is the operator has some point of control as to how much quality or what's the quality of the product that is expected to be withdrawn from the said reactor itself. So this is the downside for the batch reactor, aside from the fact also that it can only process small amount of material. If can only process a small amount of material, then of course we can't expect that the product that will be produced is also big. It will also be small. So that's in terms of the batch reactor. Now, if we're going to compare the mixed flow reactor and the plug flow reactor for first and nth order reactions, in terms of sizes, of the size of the reactor for a particular degree of conversion. So this would be the performance equations that you'll be using. You know this performance equation already. So the subscript M is for the MFR and the subscript P is for the tubular reactor. So you can see that you already have an integral to process here. Now, you may wondering why when we talk about reactor size, are we going to still have the same expression for the performance equation? The performance equation, class, in the sense is this really. So you cannot do anything about it because it's already the pre-derived formula for the performance equation for these two reactors. Now, if you need the volume or if you need the size of the reactor, you can just rewrite the taus that are written here on the left side. So we know that the tau is V over VO. Then you can write this for the MFR as V over VO. The same thing with the tubular reactor or the plug flow reactor. But the way we write the performance equations, it's always in terms of the time it would take for one reactor volume of feed to be processed. That's how we measure the performance of these two flow reactors. So that is why it's always in terms of tau. The second set of formula that you are seeing below is for nth order reactions already. So meaning it could be 1/2, it could be decimal, it could be fraction, it could be negative even. So all you have to do is appropriately write here the n, the appropriate n for the formula. For your plug flow reactor, this is your formula for any nth order reaction. And this is how you determine the size of the two reactors given, of course, it has to be given the degree of conversion. You cannot determine the size of your reactor if you're not provided with the desired degree of conversion of your reactant into product. So this is in the case of the MFR and the PFR. Our book has a graphical approach in determining the ratio of the volumes of the MFR to PFR as written here on the vertical axis of this particular graph. No, though I don't suggest that you use this particular graph because in terms of epsilon values, it's not complete. What do I mean by not complete? So I will take, I will annotate. So you see, let's take for example, for the set of first order reactions. So you have this, cannot be seen class, wait. Only here, not including that bold line class. So this is only for your first order reaction. Now, for your first order reaction, given the degree of conversion, if you're going to compare the size of the MFR to the PFR or vice versa, you need the conversion because in here on the horizontal axis, you have 1 minus XA. So meaning if your degree of conversion is 90%, 1 minus 0.9 is 0.1. So this is the value that you're going to look into, or this is the line that you're going to project going up depending on what is the epsilon and what is the order of the reaction that we're talking about. Giselle? Now, you could see on the vertical axis the ratio of the initial concentrations. You could see the volumes, and you could see the FAO. Now, you see these two as a ratio. So if we're processing the same amount of feed, the same identity of feed material, just in different reactors, the CAOs here and the FAOs will just cancel each other. They will just cancel each other, and what remains is just the ratio of the volumes of the mixed flow and the plug flow reactor. So if you have the ratio of the two, then you can see which of the two will require a bigger reactor for the same type of reaction and the same degree of conversion required. But this is graphical. Now I'll go back to what I'm saying. I'm selecting this particular area here in your graph. And let's say, for example, for a 90% conversion, so your 1 minus XA is 0.1. So you need to go up until you reach the appropriate curve here or line. Now, this is for a first order reaction in which your epsilon A is equal to 2. So your epsilon A is equal to 2 for this upper curve here in the group. This one is for 1. This one is for 0. This one is for negative 1/2. And this one is for negative 2/3. So what remains a question is, what if our epsilon is not stipulated on the curves that are given in this group of curves for first order reaction? That needs you to approximate. So let's say if your epsilon A is 1.5 and this is 2 and this is 1, so 1.5 must be in between these two. And that would really be very cumbersome. So I still suggest that you go analytical, but nonetheless, this is how you should use the graph. So you have for first order here, this one is for n equal to 0.5. So now you do not know what was the corresponding epsilon. So this one is for epsilon or epsilon A equal to 0 if you're going to ask me. And there are no other curves here other than epsilon A equal to 0 for order equal to 1/2. If the order is 1/4, this will be your curve. If order is second order, this would be the group that you're going to look into. If order is 3, this is the only line that you have on top. You have the same graph in your handbook. Your handbook has this one, but I have not checked with the current edition, the ninth edition, if it is more comprehensive than this one that is shown to you, because this one is taken from Levenspiel. The one in the handbook probably is more comprehensive than the one you are seeing here. But the downside of using this, as I've said, is that it, of course, is dependent on your approximation, especially if the epsilon curve that you're looking for is not the ones that you could see in the graph. So given the conversion, you will now be able to get the value of the ratio of the volumes. So actually what you're going to read on the vertical axis is just the ratio of the volumes of the mixed flow to the plug flow reactor. So which of the two will be bigger in terms of size for the same conversion and for the same feed information. So the same CAO and the same FAO. So this is how you should use this particular graph that is provided in your book by Levenspiel. Now from this particular graph, I'd like to clear the drawings. From these particular graphs, Levenspiel gave us, shall I say, generalization. So there are generalizations that we can take out from that particular graph. Now, what will happen if you did not use the graphical approach? You can still use the analytical approach. However, the analytical approach will separately require you to solve for the volume of the MFR, then separately determine the volume of the PFR, and then compare the two values that you got. The graph, if the epsilon is already there, will give you right away the ratio of the two volumes. So it would tell you which of the two reactors will be bigger in size in terms of comparison. But nonetheless, the generalization here that Levenspiel already summarized in terms of the values that we're getting from the graph will tell us of which of the two reactors will be requiring a bigger volume for the same feed processed and for the same degree of conversion. So number 1 says here, for any particular duty and for all positive orders, meaning we're not talking about N which is negative, the mixed flow reactor is always larger than the PFR. What does this mean? I have, let's say for example, I require a degree of conversion of 0.9. In terms of the size requirement, the PFR will always require a bigger size of reactor compared to the MFR to produce the same amount of product with the same degree of conversion. So take note of this. As long as we're talking about orders of reactions which are positive. So for any particular duty and for all positive orders, MFR is always larger than the PFR. The ratio of the volume, take note, increases with the order. So from order 1 upwards, going up, the value is increasing, the same volume ratio increases. So the bigger requirement for reactor size for the MFR when we speak of bigger order of reactions if compared to a PFR. For zero order reactions, take note of this, reactor size is independent of the type of flow. What does this mean? The size or the volume for an MFR or a PFR, if we have a zero order reaction, is independent of the type of flow. So meaning the same lang, hindi siya affected because we're talking about zero order reactions. So take note of this for all positive orders only. The MFR is always bigger than the PFR. Now, when we speak of conversion which is small, the second generalization, the reactor performance is only slightly affected by flow type. So meaning, when we speak of, we're still comparing, we're comparing the MFR and the PFR. But when we speak of just smaller degree of conversion, let's say a 0.3 or a 0.4 4 or 40% degree of conversion, if we're going to compare the size of reactor that will produce the same amount of conversion for the same product produced, there isn't much difference in the size requirement. Hindi siya masyado affected. When we speak of conversion that is small, it's only slightly affected by the flow type. The volume ratio approaches unity. When we speak of unity, the ratio of the volume more or less would be equal to 1. Like I'm talking about V sub M to V sub P as conversion approaches 0. So there isn't much, just like in here, we go back to this one, just like zero order reactions. So if conversion is very, very small, it's like we have the same size requirement for the MFR and the PFR. Okay, for conversion that is very small. So as conversion approaches 0, the volume ratio approaches unity. So the same size requirement. The ratio increases very rapidly at high conversion. So as we increase conversion, the size requirement also increases in the same way as we increase orders, positive orders, the size requirement also increases. The size is more or less the same if conversion is very small, as in approaching 0. Okay, now we proceed. Okay, third, density variation is only of secondary importance to type of flow in design consideration. So take note, the epsilon, this has something to do with density variation. The epsilon is only of secondary importance to type of flow. So meaning, when we speak of size requirement class, the number one thing to look into is the type of flow. Is it MFR or is it PFR? Secondary na lang ang effects ng expansion factor. Doesn't mean that it does not have any effect, but in terms of the type of flow, it only plays secondary role in terms of sizing. So density variation is only of secondary importance to type of flow in design consideration. So let me annotate. So this one, density variation is only of secondary importance. Now, as density decreases, and that's the case of expansion class, when density decreases, meaning it's getting lightweight and lightweight, behaving more or less like a gas, PFR is more effective than the MFR. The reason why the PFR is primarily designed for gaseous reaction is because of this. As density decreases, expected is there is expansion, your PFR is more effective than an MFR. While as density increases, so if it's getting heavier in the case of liquid reactions, MFR is more effective than PFR. From in here, you could already see the significance why the PFR is preferred for gaseous reactions and the MFR is preferred for liquid reactions. Why? Because liquid tend to be more dense or is denser than the gas. Okay? For any given duty, the ratio of the sizes of the mixed and plug flow reactors will depend on, so these are the three factors in which the size or the volume of the mixed flow and the plug flow reactor will be dependent on. So number one is the extent of reaction. When we speak of extent of reaction, that has something to do with what? When you speak of extent of reaction, that has something to do with what, Jacel? Is Giselle around? When you speak of the extent of reaction, it has something to do with what?
Miss.
Yes?
Conversion, miss.
Conversion. Okay. The stoichiometry is a factor also to consider, and the form of the rate equation. So when you speak of extent, that has something to do with conversion. Stoichiometry, you know what stoichiometry is, the reaction and the rate law and the form of the rate equation. These three is very important when we compare sizing requirements for the MFR and the PFR. The reason why the rate equation is a factor to consider in comparing sizes for the MFR and the PFR, it's because you could see that the rate law is dependent on the order of the reaction. And it's number one in the generalization. As we increase the order of the reaction, there's also a bigger, shall I say, difference in the size requirement for the MFR and the PFR, in the sense that your MFR will really be a lot bigger compared to your PFR. So these are your generalization from this particular graph, from the graph that was shown to you a while ago in comparing size requirements for the two flow reactors. Now, as to design application, so let's go to this particular sample problem. So the aqueous reaction A plus B forming the products has this particular known kinetic. So 500 C sub A C sub B is to take place in an experimental tubular reactor. So experimental tubular reactor assumed to be behaving like a plug flow reactor under the following conditions. So the volume is given, the volumetric flow rate is given, and the concentration initially of the reactants in the feed. So concentration of reactant feed is this one, CaO and CbO being equal. Now, you are required for the following information. What fractional conversion of reactants can be expected? So in here, you need the XA. Now for B, for the same conversion, in A, whatever is the XA that you have determined here, what size of stirred tank reactor? So this time, you will facilitate the same reactor with the same conversion to a CSTR or a mixed flow reactor. So what size of a mixed flow reactor is needed? What conversion, letter C, can be expected in a mixed reactor equal in size to the plug flow reactor? Okay, that was solved in here. Uh, that was actually not solved but equal in size to the PFR that is given. The size is already 0.1 liter. So we have three unknown information here to determine based on the given. So I will just take a picture of that so that when we go to our solution board, we will not go back to the slide. Okay, so we'll go to our board. So this is our first sample problem. If I'm not mistaken, we have 7 in this particular set of slides. So first sample problem, for this time, we have not yet considered a system of reactors. We are simply comparing sizes in terms of conversion. So let's go to what we can take out from the provided information. So I will read a portion in the problem. You tell me what we can write down. So the aqueous reaction A plus B forming the products with known kinetic negative R sub A being equal to 500 C sub A C sub B is to take place in a tubular reactor under the following condition. So I will write down the tubular reactor here so we can save time because I may not finish. So I'll just do the illustration. So this is our tubular reactor. Your reaction, so you're provided with the stoichiometry. This is needed. Remember, in the generalization, we need the stoichiometry. So A reacting with B to form the product or products of reaction. You have a feed here and you have the processed feed here. Now, the rate law, I like to write it here, is 500 per mole per minute, liter per mole per minute, C sub A, C sub B, and it's going to take place in a tubular reactor. Now, this tubular reactor has this volume. The volumetric flow rate, I'd like to write it here, 0.05 liters per minute. And the initial concentration. The initial concentration of A and B in our feed is the same or equal at 0.01 mole per liter. So that's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 5 given information, and we are required for the following. So letter A, so I will read, what fractional conversion of reactants can be expected? So this is a PFR and you are asked for the conversion. Okay, that's letter A. Letter B, for the same conversion in letter A, what size of stirred tank reactor is needed? So with XA in A, so meaning you're going to use the degree of conversion for the PFR, you are required to determine the volume of the MFR. Meaning same reaction only facilitated in a PFR. And letter C, what conversion can be expected in a mixed reactor equal in size to the plug flow reactor? So meaning with Vm equal to Vp, so I'd like to write here Vp, you are asked to determine the degree of conversion in the mixed flow reactor. So I'd like to write this degree of conversion here with XAP. That way we can differentiate and compare degrees of conversions and sizes later on. Okay, based on what we are provided in here. So far, do you have any question as to the things that I have placed in here? I will have this paused for a while because I have a lot of message to read from your classmate. Give me a minute or so. Okay, some have okay. Okay, we have this, so we'll have the next sheet. Some have burnout, some have connectivity issues. Okay, now I will ask you. You are asked to determine the degree of conversion in the plug flow reactor. Okay, all of these are given. So how will we solve this problem? I will start with the what. Any suggestion? So for letter A, what do I start with here? What do I write first? I want the degree of conversion in the plug flow reactor. I will start with the, any suggestion? We're actually repeating the procedures that we have been doing. So what I will,
Let's use the performance equation, miss.
okay, so we will use the performance equation for the PFR because initially we have the PFR here. So the performance equation for the PFR is you have the tau. So I'd like to specify that as tau P. Then you have CAO, the integral from 0 to XA of dXA over the rate. Okay? Now, we are asked for the conversion. So meaning this particular integral will be processed because XA is the unknown. So you have to do the integration, not rely on what's in the calculator. So for the VP, that would be the tau P rather, that would be the volume divided by the volumetric flow rate. And you have the CAO, and you have 0 to XA, and you have dXA. And for the rate, you have it here. So the rate law was given to us. So I will write it down in here. So I have 500. So C sub A, C sub B. So since Joshua is very keen on looking into the units, please check my units later on Josh. Okay. Now we have this one. Now, the volume of the plug flow reactor is 0.1 and the volumetric flow rate is 0.05. So we will substitute it here. 0.1 divided by 0.05. The CAO is 0.01. And I will have here 0 to XA. Then I have here dXA. You can actually write the 500 in here. And you will have to express the CA and the CB in terms of XA. Because your variable here is XA. So you can write this as CAO 1 minus XA. And you have here CBO 1 minus XB. Okay. Now, this you can process as one number, like transfer the 500 here and transfer the 0.01 in the denominator and process it into one quantity. Can you please give me the value? So 0.1 times 500 divided by 0.05 divided by 0.01. What's the answer?
100,000, Miss.
100,000. Thank you. So you have 100,000. Okay, so you have 0 to XA. Now, if you notice this and this are the same. So this one, the CBO 1 minus quantity 1 minus XB is our problem because your variable here is XA. But I'd like to write here that CAO is equal to CBO. And that in terms of stoichiometry, CAO XA over 1 is equal to CBO XB over 1. Where are you getting that, Miss? So it's taken from this one. So we can say now that CBO XB is just equal to CAO XA. Now, if you have this expanded, that would be CBO minus CBO XB. So I'll say, therefore, CBO minus CBO XB is equal to, I write it here, CAO minus this one is CAO XA. So they're just the same. So I can rewrite this one as, in simplified form, as DXA over CAO squared 1 minus XA squared. Why is this squared and why is this squared? It's because the CBO quantity 1 minus XB, which is this one, is this. And this one is this. So we have it squared. So the CAO that we have, which is 0.01, we'll have another sheet. So you have 100,000 CaO squared. We transfer this one there, and you will be left with the integral from 0 to xa of dxa 1 minus xa squared. So if you process this integral, I know you know how to process that one. That would be 100,000 times point. Is it 0.01 or 0.1? 0.01. So this is 0.01. We square that. And if you integrate this, that would be the negative of negative 1 over 1 minus xa. Because this one would be negative 1 over negative 1. This negative is for this one. Okay? Your limit is 0 to xa. So negative, negative, that makes it positive. And the left side here will take 2 4 zeros, 10. And this one, please check. This one would be 1 over 1 minus xa minus 1, because that's 1 over 1 minus 0. Okay? So you have a 10. You have 1 minus the quantity 1 minus xa all over 1 minus xa. So I will have a 10 minus 10 xa here. This one transfer there. This one will cancel each other, and you have xa in the numerator. So your xa P for your plug flow reactor is equal to, so that would be 11. 10 over 11, right? 11. And that would be in decimal. Anyone?
0.909.
0.909. Okay. 0.909. So this is the answer for letter A. Look at it. Very high degree of conversion for your plug flow reactor. Okay, 0.9. Thank you for the answers, ladies. So you have this one. Now letter B. Letter B. So in letter B, said there, what if I will use the same degree of conversion in A, but I will facilitate the reaction in a mixed flow reactor. Okay, so I will solve for the volume requirement for a mixed flow reactor that will have the same degree of conversion as the plug flow. So you go back to the performance equation for the mixed flow reactor. Now, performance equation for the MFR is, anyone? CaO XA over the rate. That's it. The same volume, but this time we will solve for the volume of the plug for the MFR. And the same volumetric flow rate, the same initial concentration, the same degree of conversion as stated. We will use the degree of conversion of the PFR. Then we will have here 500. This is CaO squared 1 minus XA squared. We have already determined why our CaCb is equal to this. Okay? We will cancel this. This leaves us with 1 here. And that is our degree of conversion. Now, volume of the mixed flow reactor is equal to the volumetric flow rate is 0.05. So this is 0.05 and transfer there, and you will multiply it with 0.909. We divide it by 500, and we still have 1 CaO here, which is 0.01. And this one is 1 minus 0.909 squared. The volume of the mixed flow reactor that will acquire the same degree of conversion in terms of size requirement, the same amount of product, the same size, the same conversion is
1.1, Miss.
1.1. Thank you, Jess and Katrina. So 1.1. 1.1 liter. Okay, I'd like to place this in a box. Compare. Look closely. The volume of the plug flow is just 0.1 liter. And we're just talking only of a second order reaction here. Look at the difference of the volume of the reactor requirement. Very big. 1 liter. The one is just 0.1 liter in volume. This one is 1.1 liter. More than 100% pilaka percent over bigger ang mixed flow reactor. This is just but a second order reaction. So how much more if this is third order? Okay, so even a bigger difference in the volume requirement. So our answer for letter B is 1.1. So letter C, we go to letter C. So for letter C, you are required to, what's required for letter C? The same volume as the mixed flow, what is, you use the same volume of the plug flow for the mixed flow, what is the degree of conversion? So meaning, you will still work with the performance equation of a mixed flow reactor, but you will use the volume of the plug flow, which is just 0.1. Okay, so this is what we're going to do. So it's still tau CaOXA over the rate. This is still V, but I will use the volume of the plug flow as it's stipulated there. I will have the VO. I will still have CaOXA. Now I will determine the conversion here. I will have 500. I will have CaO squared. And I will have 1 minus XAM squared. The volume of the plug flow is just 0.1. So meaning, what if we will use a 0.1 liter mixed flow reactor? What is its conversion? Okay, this one is 0.05. Okay, let me check. We got 0.05, correct? And we have here, we cancel this. We still have 1 here. We have XAM. We have a 500 here and a 0.01 here and a 1 minus XAM squared. Now, you will be like, you will get a conversion which will really be incomparable to the degree of conversion of your PFR. Can you solve for XAM? 0.73. Thank you. So 0.73. Remember, this is the degree of conversion for your MFR compared to the degree of conversion for the plug flow, which is 0.909. So see, the plug flow is really efficient in terms of product quality, though the volume requirement is very small. It can only process a small amount of volume, but the quality, look at the degree of conversion. The MFR can process a bigger volume, but the conversion is small. Okay, so you can see that if I will process a smaller volume for my mixed flow reactor, this is just the conversion. This is the conversion for the PFR. So now you are able to, thank you for the values, you are able to compare which of the two is bigger in size requirement, and which of the two has a bigger degree of conversion. So in terms of comparing how an MFR performs compared to a PFR. So I will have to stop sharing here now. So we have answered the three required information there.